to prove this inequality holds for a, I, b, I are real numbers, ci is positive, I 1 to all the way up to n. But first, we construct a quadratic equation, because to prove, I'll denote as a, b, and c. So to prove that a times b is greater than or equal to c squared, all we have to do is to reconstruct a times x squared plus 2c times x plus b greater than or equal to 0, 0. Can we prove this? Because if that's the case, then we can immediately say, okay, we also have to prove a is strictly positive. Right? So that the way the graph of this quadratic is looks like this. Right? So always non-negative. So its discriminant has to be 4c squared, 4ab has to be less than or equal to 0. Right? So in other words, 4c squared less than or equal to 4. So c squared less than or equal to ab, right? So it all comes down to proving two things. Right? Those two things. Then we're done. We'll prove this later. Right? Once we prove this will automatically be true. Right? So the reason is because, first of all, I say, so can we show that the a times, okay, can we show double sum ci plus cj, ai times aj times x squared. Right, we can easily put the x squared inside the sum plus 2c I j ci plus cj. C is that, so aibj. Put the x inside the sum plus b. Double sum. B is ci plus cj. bi bj. Always greater than or equal to 0. Right? But since this is a double sum works the same as single sum. We can just add up the general terms and then sum it up. Right, so, like I said, double sum, general term, add them up. ci plus cj, ai aj x squared plus 2 times aibj times x plus bibj. Right? Is it always non-negative? So it comes down to prove two things. I first prove this, then we prove is a is a always strictly positive? Ci plus cj, ai times aj. Right. So first, okay, so top aiaj x squared, can we factorize it? Right. If we can do ai times x plus bi times aj times x plus bj, right? It'll look like this: ai times aj x squared plus ai bj x plus aj bi times x plus bi bj. Right? So almost look like the same, right? Except twice of aibjx. Okay, aibjx, ajbix. But since we have double sum, so they may be the same. Right? The reason is because First of all, this double sum this cj 2 times aibj. This is the same as we split it into 2, right? ij ci plus cj ai bjx plus exactly the same sum. I j ci plus cj ai bjx. Same thing. Then somehow let's look at the first sum. Okay, first sum. Okay, we're going to turn it into first we sum with respect to j. Like I said, it's double sum. Right? Double sum. ci, cj, ai, bj. Now we reindex. We say change j into k. J into k. I 1 to n. K. Ci plus ck this time. Ai bj bk this time. Right? Now what? Now we change I into j. J from 1 to n. K from 1 to n. Cj, ck, aj, bk. Right? Now we change k into I. I from 1 to n. Cj plus ci aj times bi. Right? Same thing. Okay. First sum with respect to I, then sum with respect to j. Right? But this is still double sum, no problem. No matter which order you do it. Same thing. Alright, copy down. Cj plus ci. Same thing. Ci plus cj. Exactly the same. Aj bix. Right? So eventually, like I said, the first sum is exactly that. Exactly that. Therefore, this sum equal to this plus that. Right? Therefore, this sum actually equal to this plus that. So what does that tell us? Right? Double sum, double sum. Same denominator. Right? Numerator aibj, ajbi, right? aibjx, ajbix, right? Same thing, right? Double sum, right? So this double sum should equal to same bottom, top change into this. Right? Like I said, we can somehow change this top into this factorization. So in the end, can we prove this double sum is always non-negative? Ci plus cj aix plus bi times ajx plus bj. But somehow, right now, treat x as a constant. Could be positive or negative. Right now, fix x. We can perhaps denote we'll denote aix plus bi as xi. Right? It has definitely has something to do with I, also has something to do with x, so xi, some fixed real number, times xj, ci plus cj. Can we show this is true? Right. But this is kind of similar to that. We want to also prove this is strictly positive. Right. Of course, it'll be even better if I can prove this is strictly positive. But this, like I said, xi, xj, no restriction, just two real numbers. But to prove this is true, here we construct a function in terms of t. Right? That is double sum ci plus cj xi times xj times t to the power of ci plus cj. This function in terms of t. Finite sum. Finite sum, of course, it's legal for us to differentiate term by term. F prime of t. Double sum. ci plus cj cancel with this ci plus cj. So xi times xj times t to the power of ci plus cj minus 1. Right? In fact, we can put the t to the power of minus 1 as 1 over t. Of course, here we require t to be non-zero. Right? So is this always, like I said, is this, if we can prove the derivative is always positive, then it means the function is increasing. Right? But the fact is that, first of all, this double sum, how can we rewrite this double sum? Perhaps let's first sum with respect to j, then sum with respect to I. Here we rewrite it as xi times t to the power of ci times xj times t to the power of cj. This is perfectly legal. Right now, since we sum with respect to j inside, so right now we treat I as a constant. Here we simply just factor out xi t to the ci. Factor that out. 1 over t I. Just pull out this xi t to the ci outside of this sum j from 1 to n. xj t to the cj. Perfectly legal. So we reached to this part, right? So first, pull out the xi t ci. Sum this up. Then we sum I goes from 1 to n. Right, but since this is sum with respect to I, this is sum is already a constant. Take out this constant out of this sum. Right. So immediately I have 1 over t. Sigma j x j t to the cj. This is a constant pulled out of this sum. Right? That is I goes from 1. xi t to the ci. Right? So now the constant outside of this sum. So this again is a double sum. Double sum. But this sum is essentially the same as this sum, right? Dummy index I, j, essentially the same thing, right? So I goes from 1 to xi t to the ci, quantity square, right? That is the derivative of f of t. Of course, always non-negative. We reached the derivative of the f of t equal to this part, so obviously non-negative. Now, what is f of 0? Obviously 0. Right? So, since it's a increasing function, therefore f1 has to be bigger than or equal to f of 0. Is it strictly bigger than that? Right? If they're equal to each other, right? So f of 0 is equal to 0. F of 1 also equal to 0. Also increasing function, so only could be a constant function, which is not possible. Right? How can this be a constant function? Right? So no, has to be strictly bigger than that. Right? In other words, f of 1 is just, this becomes 1, so it's just this part. Right? So just this part. Right? Strictly positive. Like I said, this is essentially the same as this part, except I use some notation, xi, xj, some random real numbers. Essentially the same. Right? Eventually I prove this is strictly positive. Right? And also, this is automatically true as well. Right? Because this is essentially the same of essence as this one. Right? Just some multiple, some product of some random two real numbers, aiaj, right? Same idea, still strictly positive. Right? So this, remember, this is the a coefficient of the leading term of the quadratic I constructed in the first place, right? Course, quadratic will look like this. Right, always positive, right? Leading term, coefficient positive, right? Looks like this. So no real roots. Right? In other words, discriminant has to be strictly negative. Right? Same as to say AB is greater than or equal to c squared.